Let me start with some tips for tackling the questions in problem sets. You will be asked to solve for all Nash equilibria sometimes, and in that case, you need to show that you actually find all Nash equilibria. This means that you do not simply give a couple of Nash equilibria you find, and you need to show that there are no other Nash equilibria in a given game. And here is how to do this. First, if you are lucky and the game contains a strictly dominated strategy, then remove the strictly dominated strategy from the original game and analyze a smaller game. Second, if you see what each player's best response correspondences are, you can obtain all Nash equilibria by looking for the strategy profiles in which every player is best responding to each other. This can be done by drawing a graph that shows best response correspondences of each player and finding the intersections of these best response correspondences. Lastly, if you cannot derive best response correspondences, you can guess what the strategy profile is in Nash equilibrium and then verify that they are actually Nash equilibria. Finally, also show that there are no other Nash equilibria. We will be talking about mixed strategies. And to derive mixed strategy in a given game, we need to know the payoff of a player when rival players use mixed strategy. To this end, we defined expected payoffs of a player which players use to compare relevant payoffs when mixed strategies are played by rival players. First, we let delta Si here denote the set of player I's all mixed strategies. Then we can represent player I's mixed strategy as a probability distribution over the set of strategies Si. For example, consider the rock, paper, scissors in which the set of strategies consists of 3 pure strategies: rock, paper, and scissors. The mixed strategy sigma I here is a function that takes one of the pure strategies and maps into a probability. In this example, rock, paper, and scissors are all played with the probability of 1/3. That is, R is chosen with probability 1/3, P is also chosen with the probability 1/3, and S is also chosen with the probability of 1/3. The payoff for player I is described as the expected payoff when mixed strategy is played. And it is the expected value of her payoff where the expectation is taken over the distribution of mixed strategies. We will go through examples, and so you do not need to worry if you don't see what they mean for now. But one thing to keep in mind here is that a pure strategy is also a mixed strategy. And so the mixed strategies include pure strategies where a certain strategy is taken with the probability 1. Now, let's define what Nash equilibrium is when players use mixed strategies. A strategy profile sigma star is said to be a Nash equilibrium if the expected utility of player I cannot be improved by taking some other mixed strategies sigma I when rival players play mixed strategies sigma star minus I. One thing to note here is that a strictly dominated strategy cannot be a mixed strategy Nash equilibrium, as in the case of pure strategy Nash equilibrium. And so iterated elimination of strictly dominated strategies can also be applied to derive mixed strategy Nash equilibrium. We saw that pure strategy Nash equilibria can be thought of as a strategy profile in which every player best responding to each other in pure strategy. We can also apply this to the case of mixed strategy Nash equilibrium and think of mixed strategy Nash equilibrium as the strategy profile where every player is best responding to each other in mixed strategies. Let's see if we can find a mixed strategy Nash equilibrium in example 1. In this game, there is no pure strategy Nash equilibrium. You should try and verify that is the case if you do not see that the game does not have any pure strategy Nash equilibria immediately. We first define what a mixed strategy is in this game. To do this, we let Pi denote a probability that player I takes strategy H in her mixed strategy. Note here that P1 represents the whole distribution of player 1's mixed strategy in this simple game, since we know the probability of playing T once we know the probability of playing H. That is, we know 1 minus Pi once we know Pi. For example, if P1 is 1/3, this means that player 1 plays H with probability of 1/3, but this also means that player 1 plays T with probability of 2/3. So we only need to figure out the probability of playing H for the two players in a Nash equilibrium. Given that the mixed strategy profile of player 1 and 2 can be completely described by P1 and P2, we can now define what the expected utility of each player is. For example, a player 1's expected utility is a function of P1 and P2, which is shown on the slide. Now, let's look at the components of the expected utility. The first component, P1 times P2, is the probability that both players choose H. When both players choose H, player 1 gets the payoff of 1, and so the two probabilities P1 and P2 is multiplied by 1. Similarly, the second component, P1 times 1 minus P2, is the probability that player 1 plays H and player 2 plays T. When the two players choose different strategies, player 1 gets the payoff of -1, and so the payoff is P1 times 1 minus P2 times -1. We can go on to exhaust all possible combinations of strategy pairs to define the expected payoff of player 1 and 2. We now simplify the expression of the expected payoff in terms of P1, and since player 1 is going to choose P1 to maximize his expected payoff. Now, doing a bit of algebra gives you the expected payoff of player 1 as a linear function of P1. This means that the expected payoff of player 1 is linearly increasing or decreasing or not changing at all, depending on the value of P2. We now consider each of the three possible scenarios to derive best response correspondences of player 1 in this game.